Hey there, and welcome to 3.3 on complex numbers. What we're going to look at today is talking about one particular standard, and that's NCNS1, and that's knowing that there's a complex number such that I squared is equal to -1, and that's what we're going to talk about here in a second, and that every complex number is in the form of a plus bi, with a and b being real numbers. And so that's what we're going to talk about here. And so our objective is to be able to perform operations with pure imaginary numbers and operations with complex numbers. But before we can talk about what is an imaginary number, we need to talk about the real number system for a second. So if you remember back in the good old days, all of the numbers that you knew fit in this box. They were real numbers, right? So 7, -9, 1/2, pi, all those numbers fit into this box. But there's a whole nother set of numbers that exist outside of the real numbers. And those numbers are called imaginary. And so these imaginary numbers are numbers that come up because of this following property. If you remember, we can take the square root of positive numbers all the time. We can take the square root of 4 and get what? 2, right? But if I try to do the square root of -4, what does it come out to? Well, that's an issue because there's not a number times itself that equals -4, because a positive times a positive is a positive, and a negative times a negative is a negative. And so what we have derived is what we call imaginary numbers, and that's what allows us to continue calculations with what we call imaginary roots. And so the imaginary unit I is defined such that I squared is equal to -1. And if I squared is equal to -1, that means that I, square root of both sides, right, would just be equal to the square root of -1. And so that's the definition, that I is equal to the square root of -1. Now we're going to talk about a couple more i's, because i's are going to be periodic. And so I cubed would be I squared times I, and so that's going to be -1 times I, which is just -I. And then I to the 4th would be I squared times I squared, and so that's -1 times -1, which is +1. And so what we get is this, is that every 4 powers of I is just 1. And we're going to look at some examples of this in a second on how to simplify these higher powers of I. And so let's look at some square roots first. Let's take the square root of -28. Now, let's think about what we would do with the square root of +28 if we're simplifying this. Now, we're not talking about getting a decimal here. We can go to a calculator and get a decimal. That's not what we're talking about. When we simplify the square root of 28, we're looking for how can it break up into a perfect square and a non-perfect square piece. Well, the square root of 4 times the square root of 7 would give us the square root of 28. And the square root of 4 is what? 2. And so we're going to do the same idea, except with the negative inside. And so this is not going to split up into 2 pieces, but into 3. My first piece is going to be that -1. And then I will get the 4 and the 7. Now, all these are still under square roots. Because there is a property, and we talk about this back in Algebra 1, property that the product of the square root of m and the square root of n is equal to the square root of m times n. And because we can split out multiplication out of a radical, but we cannot split out addition or subtraction. And so splitting this out, the square root of -1, that's our I. The square root of 4 is 2, and the square root of 7 doesn't simplify. And so this ends up being 2i times the square root of 7. Now, if I were to go to a calculator and use the imaginary number, it would multiply back out to the same value that I would get if I did the square root of -28. All right, so try example B here. What's the square root of 45? Square root of -45 I'm going to simplify to. So pause the video for a second and try this one. And so when we look at this, again, it's going to split up into a couple of different pieces. The first piece is that -1. But how can 45 split up into a piece that is a perfect square and a piece that is not a perfect square? And so 45 would be 9 times 5. And so again, these are all still under square roots here. The square root of -1 is I. The square root of 9 is 3, and the square root of 5 doesn't simplify. And so we're going to get 3i times the square root of 5. Pretty simple there, right? All right. So let's look at some examples of products of pure imaginary numbers. Now, multiplying these numbers together is just like we multiply anything else together, right? These are just, treat them like variables. If I did negative 3x times 2x, what would we get? Well, we multiply the negative 3 and the 2, and so we get negative 6, and x times x gives us x squared. And so why would this be any different with an imaginary number? It's not, because our properties don't change just because we have different things, right? Our properties are properties because they work for all mathematical cases. And so when I multiply this together, I'm going to get the negative 3 times 2, which is negative 6, I times I, which is I squared. But go back to our definition, go back to our standard for today. I squared is equal to what? I squared is equal to negative 1. And so I'm going to change this I squared to negative 1, and I'm going to get negative 6 times negative 1 is positive 6. And so when we multiply negative 3i times 2i, we just get 6. The product of two imaginary numbers could come out to a real number. It sounds crazy, but it's true. All right? So try example B, 3i times 5i. So pause the video for a second, try this one. And so 3 times 5 is what? 15, and I times I is I squared, but I squared is equal to negative 1, and so 15 times negative 1 is negative 15. Again, the product of two imaginaries coming out real, okay? Now, what if I don't have the i's there, but I just have regular radicals? Remember that we talked about this property before, that if I take the product of two radicals, they multiply together into one radical. The problem comes with the imaginary piece, right? We've got to deal with the imaginary first. We've got to pull this out. So the 12, think about how this gets split up. Well, the 12 is going to split up to negative 1, 4, and 3. This will split up to the negative 1 and 2. All these are under radicals at this point. And so this is our I, this is 2, this is square root of 3. This is our I, and square root of 2 is still under here. And so multiplying what's outside, I times I is I squared, so I've got an I squared. I've got a 2 outside. And under the radicals, I'm going to get 3 times 2, which is 6. But I squared is equal to what? Negative 1. And so 2 times negative 1 times the square root of 6. And that gives me negative 2 times the square root of 6. Now, you're probably asking, wait, but doesn't a negative times a negative equal a positive? Well, normally, yes, but remember, can I take the square root of a negative in the real number system? No, it doesn't come out real, right? So that's why we have to deal with the imaginaries to multiply this out. Because if I do this without the negatives, 12 times 2 is 24, and 24 breaks up to 4 and 6, and I get 2 root 6, right? And so we see that these two answers are not the same. And that's because, again, the property that a negative square root, the square root of a negative is not real. Okay? So again, I want you to pause the video here, try example D. Square root of 2 times, the square root of negative 2 times the square root of negative 6. All right, let's take a look at this answer. The negative 2 will split up to negative 1 and 2. The 6 is going to break up into 3 pieces, negative 1, and then the 6 doesn't break up, but watch what we can do here. So this becomes an I and this becomes an I, right? And this is multiplication, so I can reorder multiplication all that I want. And so when I take this 2 and this 2 and multiply it together, I get the square root of 4. And the square root of 4 is what? This pair here is just going to give me a single 2 out of the radicals, right? Because again, all these are under radicals initially. Let's look at the square root of 3 out back. And so simplifying this, we're going to get the 2 out front. We're going to get I squared because I times I. And we got the radical 3. I squared is negative 1. And so I end up with the answer here of negative 2 times the square root of 3. So I hope this makes sense so far. Again, it's not anything crazy complicated. It's going back to properties that you should remember from middle school in Algebra 1. It's just applying them in a new way with a whole new number system. Again, this is really the first time we exposed to the imaginary numbers. And so again, the concept's a little different. but the properties still apply the same. All right, and so let's look at example 3 here. Solving an equation that's going to come out with an imaginary solution. Well, how can I solve this equation? Well, I can get the y by itself, right? So 5y squared, I can subtract the 20 from both sides, so I get negative 20. Then I'm going to divide both sides by the 5, because that's our next step. So y squared is equal to negative 4. And then my next logical step would be to take the square root of both sides. Now, remember that when I take the square root of both sides, we need the positive and the negative solution, because the square root cancels the square, and so I get y is equal to positive or negative. The square root of negative 4, well, that's going to break up to negative 1 and 4, and so that's going to give me 2i, because the square root of 4 is 2, the square root of negative 1 is I. And so this doesn't give me one solution, it gives me 2, right? Because remember, a quadratic should have how many solutions? 2. But these are imaginary solutions, so does this cross the x-axis? No. And we're going to talk more about that as we get into sections 5 and 6 this and next week. All right, so again, I'd like to pause for a second, take a second to try this problem. All right, so 2x squared plus 50 is equal to 0, so my first step is to subtract the 50. Again, these steps aren't any different than what we've done before. Divide both sides by the 2, so we get that x squared is equal to negative 25. And then when I take the square root of both sides, don't forget your plus or minus in front of the radical, because you need both the positive and the negative when you have something squared. That cancels, so x is equal to positive or negative 5i, because 25 breaks up to negative 1 and 25, right? And square root of 25 is 5, square root of negative 1 is I. So our final answer is positive or negative 5i. Again, we get 2 solutions here, okay? So, complex number. What is a complex number? This is the second part of our standard. A complex number is any number written in the form a plus bi, where a and b, so these individual parts here, are real numbers, and I is the imaginary unit. And so a is the real part of a complex number, and bi is the imaginary part. And so we just saw a moment ago, we got an answer here of 5i. Well, that's an imaginary number. It's 5 times i. But now we're going to look at numbers that combine, coming back to our little box, right? We had our real numbers over here. We had our imaginary numbers over here. Now we're going to be putting a plus sign between them. I've got a real part that's coming out of here, and an imaginary part that's coming out of here, and creating one value. Now, we're not going to be able to add this together, because just like variables, can I add constants to linear terms? No, I can't add something with an x without an x. So same idea here. My real parts will be here, my imaginary parts will be here, but I cannot combine non-like terms. And real numbers and imaginary numbers are not like terms. And so we're going to look at a little bit of an interesting example here to start. We want to find values for x and y that are going to make this statement true. 2x plus yi is equal to negative 14 minus 3i. Now, it seems like a crazy complicated problem. I got 2 variables here, but how can I solve this? But the key comes back to this, is that the real part can only deal with the real part. So the 2x has to be equal to, not the negative 14 there, but the 2x, not the negative 3i, but it's equal to the negative 14. And so 2x is equal to negative 14. So I divide both sides by the 2, so x is equal to negative 7. And then for the y, well, that's in the imaginary part. So the imaginary is going to match with the imaginary. yi is equal to negative 3i. I can divide both sides by I, and I can divide both sides by I because I is not equal to 0, so I can divide by it. So y is just equal to negative 3. So my 2 answers here, because it asked me to find both x and y, the x is equal to negative 7, and the y is equal to negative 3. Again, because the real parts deal with the real parts, the imaginaries deal with the imaginaries. So try this next example. 3x minus yi is equal to 15 plus 2i. Pause the video here. And so when we look at this problem, we get 3x pairing with the 15, so 3x equals 15. So we divide by the 3, and x is equal to 5. And now we look at the I. And so let's look at the imaginary portion. It's negative yi. Don't forget that sign. Did you forget the sign? Because if you did, this is going to cause it to be wrong. And so we divide both sides by the I. And I can also divide by the negative to get the y by itself. So I'm going to divide by the negative. And so the negatives become positive, the i's cancel. Y is equal to the negatives, or the i's cancel. So we're going to get negative 2. And so my two answers, the x is equal to 5, the y is equal to negative 2. Looking at example 5 here, to add and subtract complex numbers. Again, you can only add or subtract like terms, right? And so dealing with that, we're looking at what can I get here, right? And so the real part will add, in this case, because that's the operation, to the real part. And the imaginary part, so this plus 5i, will add to this imaginary part, negative 4i. That might become the word of the day here in a minute. I'll let you know. So 3 plus 2 is equal to 5. And 5i plus negative 4i is equal to just I. And so my final answer, this is one combined answer, 5 plus I. Because what we could do, if I rewrite this out for a second, and drop all the parentheses, plus 2 minus the 4i, I can rearrange this so it's 3 plus 2 plus 5i minus 4i. So now the 3 plus 2 combine together, and the 5i minus the 4i are able to combine together as well. That's why we get one unified answer, 5 plus I. But again, it is a complex number, a real part and an imaginary part. So example B here, subtraction. So we can think of the same idea, but remember that this negative's got to go to both of these, right? So we can go 4 minus 6i minus 3 plus 7i. Rearranging these middle terms, 4 minus the 3 minus the 6i plus the 7i. 4 minus 3 is 1, and negative 6i plus 7i would be just I, so 1 plus I. Again, these are not hard, they're just different. All right, so we're going to look at example 6 here. This is a little bit different of an example, and this is why imaginary numbers come into play. And some of you have been asking, why this, why this? Well, this is one of the places it happens. It has to deal with electricity. So in an AC current that's alternating current circuit, the voltage E, the current I, and the impedance Z are related to this formula, E is equal to I times Z. And find the voltage in a current with in a circuit with a current of 1 plus 4J amps and an impedance of 3 minus 6J ohms. Now you might be asking yourself, why J instead of I for imaginary? Well, it comes back to that just electricians have a different letter representing it because I stands for some other things, and again, I's can kind of look like ones, and so J's just help them understand that it's the imaginary unit there. But we're still dealing with imaginary, right? So if you want to change this to an I, change it to an I, but just understand that in context, they use J's from day to day in their work. And so E is equal to IZ, and so multiplying these together, right? Because E is equal to I, so that is the current, so that's the 1 plus 4I, or 1 plus 4J, keeping with the variables here, amps, times its impedance, which is the Z, which is 3 minus 6J ohms. And so, and that relates to voltage. When you talk about amps times ohms, it becomes volts. And so E is equal to the product of these. So 1 times the 3 is 3. And 1 times the negative 6J is negative 6J. And then we get plus 12J. And finally, minus 24J squared. Again, remember the J is the imaginary unit that electrical engineers use. And so E is equal to 3. These two will combine, so this is a 12 in the middle, not 7. So negative 6 and positive 12 would be a positive 6J. Remember that J squared, or I squared, is equal to negative 1, and so this is minus 24 times the negative 1. And so simplifying that, we're going to get plus 24 plus the 6J. And so our voltage is 27 plus 6J, or 6I. And this would be it's the voltage, right? And so it would be in volts. Okay? questions about that? So with multiplication, again, you can distribute to both. And another model of multiplying this out, some of you might have seen this box method before. 1 plus the 4j, 3 minus the 6j. And so 1 times 3 is 3. This is 12j minus 6j and minus 24j squared. And so then we can combine the pieces this way. 3, this is plus 6j minus 24j squared. And then we, again, do the work that we did over here to get 27 plus 6j. Okay?